All right, so why don't you take a couple minutes, and we have a little sample problem for you here. We want you to produce the template function for the data definition that you see here. All right, so you've had a few minutes to think about writing a template for this particular data definition. Now the first thing you should note when somebody gives you a data definition and says write me the template function is that your template function should mimic the form of the data definition. And if we look at this particular data definition, we can see that it is a recursive one. That is, it refers to itself. So we're saying a list of card is an empty list, or it's a card appended to the front of a list of cards. So that data definition actually involves itself. This is a normal thing. It's not just something from computer science. We do this in math all the time. So this is not something unusual. Now, our template function needs to mimic this as well. We're going to do something if the list is empty. And if the list is not empty, then what we want to do is, in order to get the result or to solve the problem for n, we note that the solution to n is equal to combining n with the solution for n minus 1. And that's what our template is going to look like. Now we won't know how they're being combined, but we can just put dot, dot, dots where that is. So what you should get is something like this. There's something I want to point out, and you may have lost lots of marks for this on assignment 1 for style. I know. I've heard a lot of complaints so far about marks lost over style on A1. If you found yourself in that group, please read the style guide. As I said many times, most of you lose most of your marks in this course due to bad style. You have to obey the style guide. Anyways, on that note, If you have an identifier that is made up of multiple names, you should separate each of those names by a dash. Now, if you're coming from writing code in another language, that's going to be very unnatural because dashes aren't permitted in like IDs for any other language. And you might be tempted to use underscores. Don't use underscores. Don't use camel case where each word is capitalized. This is what we want from you. So, list of card templates. And then mimicking our data definition, if our list is empty, we do something. We don't know what that something is because this is the template. This is the framework under which simple recursive functions for this data type are built. The list is not empty, then we're going to do something with it. So we do something with the nth item, and we're going to combine it somehow with the solution for the n-1 nth items. Sorry, if you see me doing this, I'm balancing brackets. That's the template. Now this template should look very familiar to you because it's practically identical to the ones we did last class. Yeah. Oh, thank you. There we go. There's our template. All right. Now you know how to write any simple recursive function with a list of cards. So, if you have your clicker with you, let's get it out then. We have a couple of clickers for you. I'd like to point out that the key word in this sentence is could. All right, I'll give you 10 more seconds. All right. So let's see what everyone thought. Most of you said D, all of the above, and you're not wrong. There are particular formats of lists where if the third element of the list is not actually what we're recursing on, we might have just screwed ourselves over. But generally speaking, if we're following the simple recursive case, and instead of calling rest of the list, we use third of the list, then we have a type mismatch and a runtime error. Fun thing. B, does that cause infinite recursion? Of course it does. Because if you don't have a base case, then how will I know when to stop? I won't. And so we'll go forever. And C is also true. It's not that it will cause infinite recursion. It's that it could cause infinite recursion. Because if we are missing a base case and our input required that base case, then oops. So there you go. So just for the record, you will get marks if you answered A, if you answered B, C, or D. All right, one more then. You have till 1 minute to answer this one. All right. So, most of you said A. A is correct. So simple recursion is what we have in this template. Each recursive step makes exactly one step towards the base case. When we're talking about recursion on a list, that means that with each recursive step, we are removing just one item from that list, and the item we are removing is the first one. So we're always calling it on the rest of the list. Now, why is it not B? Using a cumulator. That's where you have another parameter that is used to store intermediary results. So let's say you wanted to sum a list. Instead of just producing the sum using something like this, we could store the sum in one of the parameters. And we'll see cumulative recursion soon, just not today. And what's interesting is a lot of problems are easier to solve cumulatively, but it's not simple recursion. And it's not simple because we now have multiple arguments, and the one argument supposedly is making steps towards the base case, which would be, taking the rest of the list. But the other argument's value is changing. Is it changing to affect the base case? We don't know. That's not simple recursion. All right, then we have C, the opposite of cumulative recursion. Well, you don't know what a cumulative recursion is, or many of you probably don't. And to say the opposite of it, that doesn't make any sense. Because there's more than one thing that is not a cumulative recursion. There's simple recursion, there's generative recursion, there's mutual recursion, which is all kinds of wacky. So that question doesn't even make any sense. So it's not. All right. Any questions about this one? Right. So the first class got a freebie mark, so everybody here also gets a freebie mark. And how it works is you have 30 seconds to all, without talking to each other, push the same button. And it's always fun to see the numbers change when you can see what everybody's pushing. All right. Don't worry. Everybody gets the mark. There's always someone in the room who just has got to be different. It doesn't matter. Every time I've had a course with clickers and I tell people, push A for marks, there's always someone that pushes another letter. I get it. I really do get it. To be fair, if I was the person who had to push the button, I would have chosen something else as well. All right. So, just a couple announcements then, some things to keep in mind. As I heard from our TAs, there are still 3 students who have not completed A0. Remember that if you don't have A0 done, you don't get any of the grades for any of the other assignments until you've submitted A0. So please get it in if you haven't done it. The other thing is that you should get started on A3. You've got the whole weekend to do it. And congratulations, you're all getting a mini education in graphics this term. By virtue of the fact you asked me to make some assignments up off the top of my head, I study graphics, that's my research area, so guess what pops into my head? Graphics questions. If you take 488 in 4th year, you'll find it so easy. They're not hard, okay? Not hard questions. All right, so aside from that, we left off last class talking about recursion, which we're going to be talking a lot about recursion for a lot of this course. And if you're sitting there thinking, when do we get to talk about loops? We don't. So go cry in a corner? I don't know. Loops are next class. And by that next class, I mean 136. You can talk about loops. So we've been talking about recursive functions. And in particular, we've been talking about taking a list and doing something like counting the number of items in the list, or counting the number of items in the list that match a certain criteria. For example, we could do something like write a recursive function to count how many times the number 5 appears in a list of numbers. Now, if we wanted to think about how do I solve that problem recursively, well, we think back to the data definition for a list of a certain type. And we think to ourselves, okay, if the list is empty, there are no numbers in it. So the number of times the number 5 appears is 0. Okay, we got our base case solved. What about the other step? So if I'm counting the number of times the number 5 appears in the list, I'm going to check the first number. I'm going to ask, are you a 5? And if you are a 5, I'm going to add 1 to the count of how many times 5 appears in the remainder of the list. So I'm taking the nth item and finding some way to combine it with the solution for n minus 1 items to get the solution for n. That's what we're doing. Now, if our first item is not the 5, then we are adding 0 to the number of 5s in the rest of the list. So now that we've thought about how do we think of this problem recursively, we could take our lovely, lovely list template, which by the way is right here, and we can fill it in. And it only takes a minute, right? And presumably you've got this in Racket already at the top of your file. You can copy and paste it and just fill in the dots. So we want to find the number of 5s. So we have a list. And we know if our list is empty, we figured out that we should produce 0. And if our list is not empty, well, unlike our template, which just says empty list versus non-empty list, we have 2 cases for a non-empty list. The first item being 5 or the first item not being 5. It still follows the template, but it's just how we are combining the answer for n with the answer for n minus 1 is different depending on the value of n. So what we're going to do is, if the first element of the list is equal to 5, then we add 1 to however many 5s are in the remainder of the list. Otherwise, now we could say plus 0 and then however many 5s are in the rest of the list, but adding 0 has no effect. It does nothing. So we can just produce however many 5s there are in the rest of the list. And let's run this. I'm going to change the language level back because we're not using list abbreviations yet. Let's run this again. And now we go num 5s. There we go. All right. Now we've written a lot of different functions. We've written a function last class to sum the items in the list. We wrote a function last class to count the number of items in a list. We wrote a function last class, and in this class as well, to count how many times a specific item occurs in the list. And the format of those functions is the same. The framework is the same. It's the templates framework. These are simple recursive functions. Each recursive call makes exactly one step of progress towards the base case, and we modify nothing else. They follow this template. It's one of those things where you come to the final exam and maybe you're presented with some recursive problem. We say, solve this with simple recursion, and you're like, oh God, it's an exam. I hate exams. I hate exams. And you're like, I forgot everything, but I remember the template. And so you write down the template, and then you're like, oh yes, now I remember what I have to do. I have to figure out the base case, and I have to figure out that in order to solve the problem for n, I have to know how do I combine n with the solution for n minus 1. That's what the template tells us, and then we just figure it out and fill in the blanks. But the template can also serve as a reminder to you to the form of a simple recursive function. So that's kind of fun. Now last class, I also showed you the ability to produce a new list using a recursive function. And we actually did it by recursing on a number instead of a list. And we're going to talk about recursing on numbers in a few minutes. But for now, we just want to recurse on a list. So if we look at the notes here, they actually show you a function called negate list. So I want to build a function that is going to multiply every number in my list by -1. So I consume a list of numbers and I produce a new list of numbers. We are not modifying the old list. We are producing a brand new list. Kind of cool. All right. So how do we do this? Well, we think about it first. Okay. If my list is empty, then I can't negate anything, so I should just produce empty, because I want to produce a list, not a number now. If my list is not empty, well, then I want to negate the current item and add it onto the solution for negating the rest of the list. So now we know what we have to do. We fill in the template. There's the template. It looks just like the one we have on the board, and now we fill it in. So if the list is empty, I produce empty. Otherwise, I'm consing the negated first item onto the solution for negating the rest of the list. And you're done. You just made a new list where all the elements are negated. We didn't need a different template to do it. We use the same template we had before. Now we can build all kinds of interesting questions. But before we look at some of more interesting questions that we can do with this, let's just look quickly at the trace. So these are condensed traces. The reason why we have condensed traced in our notes is because the full ones don't fit. They would be slides and slides and slides long. So we've given you a condensed trace. There are no special rules for condensed trace. You're not expected to see what rules we've applied here. We expect you to know how to do it in full. And obviously, if it came to an exam, if it takes 3 pages for you to do the stepping, I don't want to mark that. So we'll keep the stepping problems to some nice, confined, fits on a page. So you don't need to know how to do condensed trace. So the condensed trace here, anyways, we call negate list on cons 2, cons negative 12. Right? So the list is not empty, so we go into the else condition, and we're going to negate 2. So we evaluate that. Now we have cons negative 2 onto negate list called on the rest of the list. At which point then we have a function being applied to a value, so we substitute in our body there. So we've got, after evaluating your con, that is, we're going to cons 12 negative negated onto the result of negating the rest of the list. And then you have cons negative 2, cons 12 onto negating an empty list, which just produces empty, so we end up with our final result. You should be able to go through that in each nitty-gritty detail. And remember, for recursion, there's no special rules. You're just applying a function as you would normally. So no special rules for recursive. All right. Now that's kind of fun. But what if I want to do a non-empty list? So all of the functions we've written so far made the assumption that our list could be empty or contain at least one element. What if we wanted to have a data definition for a list that is not empty? Because maybe we have a function that can only operate on non-empty lists. For example, maybe I have a function that's going to compute the average grade of the students in this class. But maybe I make the requirement, the class can only exist if there's at least one person in it. So I say that I'm making the assumption that my list that is used of students that we consume is non-empty. Well, what's the data definition for a non-empty list? Because empty is not a non-empty list. So we've got to change the data definition. And because we're changing the data definition for a non-empty list, we also need a new template. And if you look through these notes and you're like, man, where is the answer? You're not going to find it. It's not in here. We'll do it on the in bracket here. But as a reference, this is the definition for a list that could be empty. We will make a tiny change to this and get the list, the definition for a non-empty list. So if I go over here and let's go into bracket, get rid of this function, we would say a non-empty list of X is one of, now my base case isn't going to be empty because this is a non-empty list. Now you might be tempted to say, well then it's X. But it's not X because X is not a list. A list of one thing is still a list. And that's our base case, is a list of one thing. Which means it's not X, but cons X empty. Now we have our base case, and now our recursive case remains the same. There we go. All done. Teeny tiny change to go from a regular list of X to a non-empty list of X. Now, here's where things get interesting. How do you write the template for this? Because before, our template, I'm being lazy with the typing of the name. What we had before was empty list, ... else, like so. But wait, that doesn't work. This template here does not work because my list, by definition, is not empty. So that base case should never be reached because my list will never be empty. How do I change this base case? So how do I check if it's a cons x empty? So you could use the cons predicate, and that would tell you if it's a non-empty list, but the problem is it also returns true for a list of 10 items. So you can't use the cons predicate. You could use the length of the list. That's not very efficient, is it? So technically speaking, we could ask for the length of the list and see, is it equal to 1? And if it was equal to 1, then we know we are at the base case and we do our base case deal here. But if we test, and we test this question for every recursive step, and our list contains 1,000,000 elements, in order to count the number of items in the list, I actually have to visit all 1,000,000 items in the list, which means I just did 1,000,000 recursive steps, and I'm going to do it 1,000,000 times. So that's not a good idea. Any other ideas? Yellow shirt in the back corner. That is exactly what we are going to do. A list of one item is an item consed onto empty. So if this is a list of one item, the rest of the list is empty. That's the only change we have to make. And you're done. We have just changed our regular list of X template and data definition into one for a non-empty list and the set template for the same thing. Okay. Any questions about this template and this data definition? All right. So, some other things to talk about, and then we're going to have some fun writing some other functions here, is we like to also deal with strings right about now. So if you remember, we talked about there being different types. So we've talked about, numbers, we've talked about booleans, we've talked about symbols. We've mentioned there's this thing called chars, characters, and we've also mentioned the fact that you put a bunch of characters, 0 or more characters together makes a string. But what's interesting is, how do you actually do anything with a string? Suppose I want to write a function that removes all letter A's from a string. How do I do that? If we were doing this in any other language, we would have some function available to us to actually inspect each of the characters of the string. We don't have access to that at the moment. But what we do have the ability is to take a string and convert it to a list of characters. So there are 2 built-in functions in Racket. You have access to them, and if you look on some of your assignments, we even let you use them. And they are string to list and list to string. And what they're going to do is take a string and convert it into a list of characters, and the other one takes a list of characters and converts it back to a string. If we have a job like let's remove the letter A from a string, then what we actually want to do is remove the letter A from a list of characters, and then convert the modified list back to a string. So, how does that actually work? So we could look at this here, which is boring, or we could do it. So let's go over to Racket, and we can do something like string to list, and then I can say ABC. There we go. Now remember that Racket represents strings with the double quotes on either side. And characters, unfortunately, are represented by this absolute ugliness, which is the pound symbol followed by a backslash followed by the name character. I know it's ugly. You're stuck with it. Now, what I can do is, if I want to convert that list of characters back into a string, I do list to string, and then let's put cons. There we go. That's not too bad, right? Okay. So now let's actually write this function. Let's write a function that consumes a string and produces a string that has no a's in it. So no lowercase a's and no uppercase a's. How are we going to do it? So we sit down and we want to write this function. But I don't know how to remove the a's from a string. And the function I'm presenting to my user consumes a string. We can't do that directly on a string, but we do know how to remove the letter A from a list of characters. So instead of solving the problem remove a's from a string, let's instead solve the problem remove a's from a list of characters. So I'm going to comment this header out here. And now let's do the other function. All right. So I want to remove a's from this list. We're going to use simple recursion. I'm consuming a list of char. So I can use the list of x template to help me here. So let's fill in, let's just plop the template down. Okay, there's our template. How do we solve this problem? Okay. If my list is empty, it contains no characters. I'm supposed to produce a list of characters. My list contains no characters. So if my list is empty, I should produce empty. Okay. If my list is not empty, then I'm going to look at the first character and I ask, is it an A? If it's an A, then I do not want it to be on the resulting list. So if the first character is the nth character is an A, then the answer is remove A's from list for the rest of the list. If the first character is not an A, then I want to keep that character. And so I want to add it onto the result of removing A's from the rest of the list. Okay. Now we have more conditions than our template has, but it's still the same form. But I have enough to fill it in now. So if the list is empty, I produce empty. If the first character of my list is equal to lowercase a, or the first character of my list is equal to uppercase A, this is where I don't want this character on my resulting list. So I'm just going to say the solution for n here is equal to the solution for n minus 1. So the solution for the rest of the list. Too many brackets. Otherwise, it's not an A. We want to keep it. So I'm going to cons it onto the result of removing A's from the remainder of the list. There we go. We're all done. And we run it, and there's no syntax errors, and everybody's happy. But here's the problem. I just solved the problem of removing the letter A from a list of characters. That wasn't the question you were asked to solve. You were asked to solve the question, remove A's from a string. Now you might be thinking to yourself, okay, so why don't we just tell the user that they have to call strings list before they call our function? That doesn't seem very nice, does it? You're putting it on the user to convert their input to the format that you want to accept. What if the person using your code doesn't know that string to list exists? And they're going to be like, are you seriously asking me to manually write this out? We don't want to do that. We still want to provide the user with that friendly function, remove A's from a string. That's okay. We can still do that. And in fact, it doesn't take much effort now. What we're going to do is we're going to create the function for the user, remove A's from string. And we are going to do the conversion between string and list on their behalf. And then call the function we created to remove the letter A from a list of characters instead. So what we're going to do is we call list to string on removing the A's from a list of characters, and we're going to convert our string into a list of characters as needed. And this function is real easy, right? It's one-liner. Yeah. This kind of function has a special name. It's called a wrapper. A lot of the time, when we are writing solutions to problems, we realize that we need a lot of extra arguments. Like, maybe I decided to compute the maximum number in a list, and I'm going to keep the maximum so far as one of the arguments to my function, my recursive function. You can solve max that way. But when I ask the user to call my max function, they shouldn't need to know what that other argument is for, or whatever those other arguments are for that specific implementation you have done. You want to present your user with a simple, clean function where they don't need to know any of the implementation details in order to use. You create a wrapper function. You give them that simple, clean interface that hides you adding extra parameters, it hides you converting the parameters to different types, and it hides you converting the produced value to another type. It wraps the actual implementation. We made a wrapper here. And this all works. See? Works just fine. I didn't need to know the implementation in order to do this. Now, a wrapper function may look like a silly little function, and you might be asking, do I need the design recipe for a wrapper function? Do I need the whole design recipe? Yes, because that's the function we actually asked you for. So it needs the full thing. Now, what about the actual body, the real meat and potatoes? Remove A's from list. Technically speaking, that's a helper function. And so it only requires the parts of a design recipe that you would use for helpers, which I think is everything but the tests. That being said, test your helpers, please. If your helpers don't work, how do you know the main one works? Now you might be wondering, what should I name the actual function that does all of the work? Should I call it remove A's helper? Very tempting to do that. Also very dumb. Why is it dumb? Sure, at the moment, I'm using that function to remove A's from a list of characters. I'm only using that function in remove A's from a string. But who's to say I don't have some other code somewhere that wants to remove the letter A from a list of characters? Do you want to call remove A's from list or remove A's helper? One of those makes sense, and one of those seems kind of silly. So to make your code reusable, having the name helper in your helper function doesn't make sense, because it may be helping many other different functions. And if you just call it this function's helper, that doesn't make me feel like I could reuse it elsewhere. So it's best practices to not include dash helper in the function name. All right. Yep. So for helper functions, we don't require a full testing suite. You still need a purpose and a contract and examples, but you don't need all the tests. However, I am recommending to you that you do the tests anyways, because you want to be confident that the helper you wrote does what you say it does before you actually use it. And how else could you be confident if you didn't do the tests? So even though we don't mark them, you should still do them. All right. Now, one other thing you might be thinking, wrapper functions are for racket only. I never said that. I write wrapper functions all the time. The language that if I go home tonight and I write code, okay, admittedly, if I'm going home tonight to write code, I'm going to write it in MATLAB, another language. But usually, if I go home and you say, hey, write me this function, I'm probably going to write it in C++. I write wrapper functions in pretty much every language all the time. You write them because sometimes you want to present the user with a very clean API that doesn't reflect the nasty implementation underneath. You write wrapper functions because maybe you want a function that can work on several different situations. And you want to switch the body of the function out depending on the situation. Wrapper functions are not unique to Racket and functional languages. You will see them everywhere. So this is an idea you should get used to. All right. Any questions about what we've seen so far? Strings, characters. All right. So with that then, one last comment about the function we've written here. So what this function did was it removed specific elements from the list. You could almost say this was a filtering function. It filtered out all of the A's from my list. Very useful function. But what if I want to filter out all the B's? Or what if I want to filter out all the vowels? Right now, in the amount of language that we have given you, anytime you want to filter a list, you're going to have to write your brand new self-made filtering function. For the record, there's also one built in Racket. There's a filter function that you can apply, and you have to tell it the condition that it's filtering on, and then you pass it a list, and it produces a new list with that condition being met. And that is a function we will get to closer to the end of the course. But just know there is a filter function. You're not allowed to use it right now. Right now you have to make the filter functions yourself for each specific case. It's a really cool function though when we get to it, and you'll see why. All right. So that's actually the end of Module 6. And now it's actually time to move on to new fun things. Which I hate to say it is just a review of the things that we just did, except now instead of doing recursion on a list, we want to do recursion on a number instead. And we've already done a sample of this. We did recursion on a number that produced a list, and maybe you don't remember it, but we're going to go over it again. So it was pretty simple or straightforward when we had our recursive data definition to build our recursive template function and make recursive functions on a list. It was all right. If I want to do recursion on numbers, I have to think about numbers in a recursive way. And that's probably going to seem like a very strange concept. How do you think of numbers in a recursive way? So we had our data definition. Here's our template for lists. What about numbers? You can think about numbers recursively. If you think about just natural numbers, or positive integers, or negative integers, you can think about them in a recursive way. A natural number is either 0 or 1 plus another natural number. Because 1 is equal to 1 plus 0. And 2 is equal to 1 plus 1, another natural number. And 3 is equal to 1 plus 2, where 2 is equal to 1 plus 1, and 1 is equal to 1 plus 0. Natural numbers can be defined recursively as well. Interesting side note to this. If you actually ever do anything in lambda calculus, which is kind of the theory behind functional languages, this is actually how they define numbers. They call them church numbers. And there's a lambda calculus notation for them. They don't define it exactly like that, but it's equivalent. They actually define numbers using recursion. That is a very weird idea, because when we think of numbers, when you teach a kid how to count, you teach them how to count iteratively. I didn't teach my daughter to count, okay, now 5 is 1 plus 4. Admittedly, I am going to teach her that because, you got to teach her a bunch of weird things, right? Most kids you teach, okay, 1, 2, 3, 4, add 1. No, it's a different way of thinking. All right. So we've got our recursive data definition for a natural number. Hey, we could build the template for this. And it looks just like the template for our list function. Couple differences. We don't have an empty natural number. Our base case is not empty. Our base case was 0. There's actually a predicate in brackets for 0. It's 0 question mark. Surprise, surprise. So if our number is 0, that's our base case and we do something. Otherwise, I want to combine n in some way with the solution for n minus 1. So rest is sub 1n, that's n minus 1. That's it. Teeny tiny change takes our list data definition and our list template to one for natural numbers. And now we see the form of doing recursion on a natural number. So, this function we've already done, but now let's actually do it from a template's perspective. Suppose we ask you to write the function where you are going to produce a list that is counting down from n. Okay? Well, if n is 0, there are no elements. Well, if n is 0, that's the end. And I want to count down from n to 0, so if n is 0, I should produce a list that contains 0. Otherwise, if n is not 0, then what I'm actually doing is appending n to the list that counts down from n minus 1 to 0. So I'm consing n onto the countdown from n minus 1 to 0. Okay? There's the template. I can fill it in now because I've thought about how do I do this. Looks just like our list function from before. Not too bad. And we could trace through this as well. And again, these are using condensed trace. So countdown 2, the first call to it is going to produce cons 2, and then we're calling countdown on 2 minus 1, so that's countdown 1. And countdown 1 is going to cons 1 onto countdown 0, which is going to produce cons 0 empty. There we go, we're done. It's pretty easy. And we could do all kinds of things like this. Maybe I want to write a function to sum the numbers from 1 to n. Well, summing the numbers from 1 to n is equivalent to summing the numbers from n to 1. I could fill this in. I could say find sum n. Now I don't say empty because it's not a list. Here I'm saying 0. Well, if it's 0, then it contributes nothing to the sum. Otherwise, I add n to the sum of the numbers from n minus 1. That's it. Gotta make sure I have all my brackets balanced, of course. All right, so that's fairly straightforward. What if I want to do something a little bit different? Like, what if I wanted to, instead of doing the full natural number range, maybe I want to do recursion over an interval. So maybe I only want to do recursion for numbers that are greater than or equal to 7. Or maybe I want to do recursion for numbers that are less than or equal to 0. Well, we could start by doing a data definition for it. So suppose I want to work with integers that are greater than or equal to 7. Well, here's my data definition for integers that are greater than or equal to 7. I say an integer in z greater than or equal to 7 is 1 of 7, so that's our base, or add 1 to a number that's greater than or equal to 7. Data definition done. I have a data definition. I can create a template from it. And now if I wanted to write a function that's counted down from n to 7, well, my base case is going to change. Instead of checking whether n is equal to 0, I'm now going to check whether n is equal to 7. Otherwise, it stays the same. So count down to 7, n. If n is 7, I produce cons 7 empty. Otherwise, I cons n onto the result of counting down n minus 1. Okay. It's great. But here's the problem with the function that we just wrote. The problem is that what if I want to count down to 5? Or what if I want to count down to 20? Or 67? Or what if I want to count down to whatever number my user wants to count down to? Are you telling me they've got to create a data definition, create a template for that specific case, and then write a very specific function to count down? Doesn't make a lot of sense. What we actually want to do is generalize this concept and have us count down from n to b. Some base case. So, we can do that. Now we could create a data definition for this, by the way. The data definition would be an integer z greater than or equal to b is 1 of b, or cons, sorry, not cons, add 1 to a number that's greater than or equal to b. So that would be the general data definition for any number greater than or equal to b. And then we could write a template for it, but this is how our function is going to look like. Because the base case, what the number is we are counting down to, is no longer fixed, now it is decided by the user, it has to be a parameter. And so what we're going to do is in the countdown function, our base case is now, instead of saying n equal to 7, it says n equal to b, where b is the base case that is passed as a parameter to the function. Else stays the same as before. We cons the number n onto the result of counting down from n minus 1 to b. Now, this is still simple recursion, because with each recursive step, we are moving exactly one position closer to the base case. Now, you might be thinking, well, I have a second argument here. That makes it not simple. But it is still simple, because the second argument does not change. For each of the recursive steps, that second argument, b, is the same value. We say it goes along for the ride. Still makes it simple recursion. Now, if I was manipulating b in some way, this would not be simple recursion. But we're not, so it's still simple. So now I can count down from n to whatever number I want. And believe it or not, this function also works for negative numbers just fine. So we don't need to change anything to do countdown from negative 10 to negative 20. We're fine. All right. Now, there's a trace in here if you want to go through it. I'm not going to go through the trace with you. Or doing negative numbers. What if I want to go the other way? What if I want to, instead of counting down, I want to count up? And maybe I want to count up from a negative number to 0. Okay? We can make a data definition for negative numbers first. So first we say an integer that is less than or equal to 0 is 1 of 0, or sub 1, a number less than or equal to 0. Okay? That's the data definition for negative numbers. And from this, we can actually count up. Why would we be counting up using this negative number definition? Because moving to the base case, which is 0, we have to add 1. We're doing the opposite. Here is our template then for negative integers. So I am going to do something when n is 0. And remember, when n is 0, that is our base case here. Stop when n is 0, because there's no longer a negative value after it. And then we say, otherwise, if n is not equal to 0, then it must be a negative number. So we are going to combine in some way n with the results of applying a function on n plus 1. Because plus is going to take us towards our base case. So it's the solution for the rest. So count up then, to count from negative 20 to negative 10, or well, in this case it's from negative 20 to 0, we take our template. If it's 0, well, we want to just produce 0. Otherwise, we cons n onto count up, add 1n. The really big takeaway from these two examples, count down and count up, is that the recursive step has to make progress towards the base case. So if we are counting down, we are subtracting 1. And if we are counting up, we would be adding 1 to move towards whatever base case we have set. Now, if I wanted to do count up to a specific number, I could write that function as well. And it looks almost identical to count down to a number, except instead of subtracting 1, now we're adding 1. That's it. That's not so bad, right? And you can do all kinds of things with this. So for example, if you wanted to solve Fibonacci, you can do that now. Now technically speaking, I don't think Fibonacci is simple recursion, but I bet you could expand upon what we've done here real quick to do it. But there's lots of other math functions we can do recursively. So we've already summed numbers recursively. Another really fun function to do recursively is factorial. So if you're not familiar with factorial, if the factorial of the number 5 is 5 times 4 times 3 times 2 times 1. Wait a minute. You're saying that 5 factorial is 5 times 4 factorial. And 4 factorial is 4 times 3 factorial. That's counting down. That's simple recursion. We can do this. It's real easy. So let's write that function. So, now here's the tricky part. The base case is 0, but factorial does not multiply anything by 0. Because then any number factorial would give us 0. Realistically speaking, we stop at 1. But if we look at our definition of natural numbers, that's not our base case. But that's okay. We can still use 0. It's just instead of producing 0 when n is 0, we're going to produce 1. So I produce 1. Else, multiply n by factorial of sub 1 n. There we go. Factorial of 2 is 2 because it's 2 times 1. Factorial of 5 is 120. Now, you might be thinking to yourself, you're going a step too far. You multiply it by 1, and then you still make a recursive call on 0 to multiply it by 1 again. So we can, in this case, to reduce the number of steps that we take, we could change our base case here to that. It would be a little bit faster, not noticeably so. So you have lots of power in your hands now to write all kinds of math functions using recursion, working with list with recursion, taking a list, producing another list, taking a string, manipulating the string, and producing a new string. You've got all kinds of tools at your hands now. I want to show you something really fun, though, before you go. What I want to show you comes back to one of our first lectures where we talked about values in Racket. We talked about integers and numbers in Racket as being unbound. Now, if you're looking at a language like C or C++ or Java, there's a bound to the value an integer can have. A 32-bit integer can be between negative 2.1 billion and positive 2.1 billion. 64-bit integer, you get a little bit more space. Racket does not have such limitations. Now you might be wondering, why would, who cares about the limitation? Nobody has a number that big. Why would you ever end up with a number that big in a program? Okay. So I want to take you back in time then to why these bounds can be a serious problem. How many of you had the first generation Xbox? A couple people. Okay, I don't remember when that was released, to be fair. But the first generation Xbox had a snowboarding game on it. And I'm seeing you nod your head, you know what I'm talking about. So the snowboarding game had a score. And the score was stored in an integer that had a rather low bound on it. And one of the interesting things about integers that have bounds is that if you go over the bound, they go negative. So you could be playing this snowboarding game and you get this really high positive score, really shitty negative score, and you're like, what? What the hell just happened here? This is a problem for languages where numbers have bounds. You might do some math equation that exceeds the maximum number, and then what the hell are you supposed to do? Now, why this is and how we handle it, that's not covered in this course. That's courses later down the road. But Racket doesn't have this bound. Racket doing numbers is also not terribly efficient, but it doesn't have this bound. What does that mean? Let me show you what that means with factorial. So factorial is rather interesting, and numbers get very big very, very fast. Factorial of 10 is already 3.6 million. What do you think the factorial of 100 is? I don't want to be here for the next 100 years. Okay. Try to do factorial of 100 in C. Guess what? Ain't gonna work. It's gonna give you a wonky, stupid number because you went out of bounds of integer. Racket didn't. Is that not big enough for you? Let's do factorial of 1,000. Still not enough? There's 10,000. Still not enough? And you're like, what the hell is going on here? Okay, so theoretically speaking, Racket has no bounds on numbers. And this will work, but it will also fry my computer, so I will have to kill it shortly. Not fry my computer. Let's just say Racket's using 100% of my CPU's resources right now. Racket theoretically has no bound on integers, but your computer has a fixed amount of processing power and a fixed amount of memory. And Racket could theoretically run out. I could leave this running here for the next little while and it's going to keep going. So even though they say it is unbound, and you might think to yourself, great, I can do factorial of 1,000,000. Please don't. You're going to have your computer run out of resources. What do I mean by that? Okay, so let's go over. I'm on a Mac, so this is a command you can use in any Unix-based operating system. And let's do this command called top. And Dr. Racket, there you are. Dr. Racket is using a very significant part of my CPU. Yes, I know OBS is using more. That's the streaming program. Dr. Racket is also using over 1 gig of memory. And I bet if we sit here, it's going to go up and up and up. And eventually, I'm going to run out and the program's going to die. Yes, numbers are unbound in Racket. But if you're trying to use ridiculously large numbers, don't expect your performance to actually be very speedy. So don't do this. I'm going to kill Dr. Racket here. Yeah, you can see it just shot up. It's using 1.08 gigs now. Okay, so 79285. 77285. There we go. Racket's gone. I killed it that way because I don't want to sit here for the next 2 hours waiting for it to finish. Be careful. If you accidentally write the factorial function and you have infinite recursion, A, you'll have infinite recursion and run out of stack space or memory, and B, even if you didn't run out of memory, you end up in this situation where it's using all of your computer's resources and running for a really long time. So be careful with this. All right, I'm going to end it there. We will start Module 8, I guess, next week.